Okay, I guess without any further ado, are you ready, Mervyn?
So yes, from me.
Good. Okay, I guess we'll make a start. Well, good evening, everyone. A very warm welcome indeed to another Sussex Universe lecture. Seems like a long time since we did one of these. I hope everyone is keeping well, and thank you for joining us. Tonight we have one of our PhD students at the University of Sussex in the Department of Physics and Astronomy, Mervyn, and he's going to be talking about the work he does at CERN and at the Large Hadron Collider. So yeah, sit back, relax, and I believe there will be some kind of interactivity during the talk as well. Is that true?
That is the plan.
Yeah,
See how it goes.
everyone loves a good Q&A session.
Yeah.
Well, a voting, a polling session. Okay, without further ado, take it away.
Thank you, Darren, and thank you all for coming. I'd love it if you turned your video on because it's very nice to see faces at the moment. And please, if there's anything that comes up, any questions, please type them in chat. And you're also welcome to unmute and shout out if they don't seem to be being taken into account from the chat, don't seem to be being answered or whatever. So yes, I'm going to answer this question, what makes CERN special? And I have 4 answers to that question. Hopefully the 4 different answers will be clearer as we go through the presentation. As Darren said, I'm Mayron and I'm a physicist at CERN and the University of Sussex. I'm going to start by asking, what is CERN? And you may have heard that it's something to do with nuclear, but I've got a question for you. Which of these do we do at CERN? So I'm going to flash up a few answers and you can type them in chat like a yes or a no. Do we do nuclear energy? Do we do nuclear weapons? Do we do research into the nucleus? So take a moment to think about those. Or if you're watching on YouTube afterwards, you can pause to think about it a bit longer. So I'm going to start revealing answers. You can keep them coming in. I think you know, we don't do nuclear energy. Other labs focus on that. We don't do nuclear weapons. It wouldn't make sense for any of the people involved with CERN to make nuclear weapons because they collaborate with people from different countries. So those other countries would know their plans for the nuclear weapons, so it wouldn't make sense. And it's not what we do anyway. But we do research into the nucleus. So I think everyone got that. Now, at CERN, we answer questions to try and do this research into the nucleus, such as what is matter made of? Now, this is a bit of a journey through history in that 2,500 years ago, the ancient Greeks thought that atoms were the smallest pieces of matter, the smallest building blocks of everything around us, the chair you might be sat on, your body, my body. But in the 120 years ago, it was found that atoms could be broken up into electrons and a nucleus. And then 100 years ago, it was found that a nucleus could be broken up into a proton and a neutron, or in fact, multiple protons and neutrons. And then about 50 years ago at CERN, it was found that protons and neutrons could be broken up into even smaller things called quarks. Bit of a funny name. Now, I've got another question for you. This one's just your opinion. Do you think there's anything smaller than a quark? Is there anything smaller? One possible answer might be yes, we haven't discovered it yet. It exists, but we haven't discovered it yet. So type in chat what you might think. No, we've definitely found the smallest thing there is. Or possibly a third answer, I've got no idea, but CERN will definitely help find the answer. So again, if you're watching on YouTube afterwards, you can pause and have some more time to think about it. There's no wrong answer with this one, so keep them coming in. It's interesting to see a mix of answers so far. We've had all of them. We've had 1, 2, and 3. Most people going with 3, I think. 3 and 1. I wonder how that works. Okay, thanks very much for your answers. I would probably go with 3 if I had to give an answer. But as I say, we don't know. That's something we're actively trying to answer. Another thing we do at CERN is checking theories. Now, this is what we call the particle zoo, which are all of the matter particles we know of have found so far. They each have these funny little characters, and these characters can often say something about the particle themselves. For example, the neutrinos look a bit like ninjas because they hardly interact with other particles. They sneak past them. So there are these 12 here, but in fact, only the top 4 we see in the matter around us, in the chair, your body, my body. The others don't live for long enough to be seen around us in everyday life. They only get created in places like CERN and then quickly die and turn into these ones in the top row. And those are the matter particles, and there are also particles to do with the forces of nature. Also got some funny names. We've got the gluon, which is the particle of the strong force. We've got the photon, the particle of the electromagnetic force. We've got bosons, W and Z bosons for the weak force, and an as yet undiscovered particle called the graviton. It's for the moment hypothetical because we haven't proven that it exists, and it would be the particle corresponding to gravity. And there's also a last piece of the puzzle called the Higgs boson. Like I said, at CERN, the main thing we do is answer questions about the universe, such as why is there so much more matter than antimatter? Where has all the antimatter gone? Another question is, can we find a particle corresponding to dark matter? Astronomy and cosmology friends of mine in the Department of Sussex tell me that there's a lot of dark matter, but we haven't found anything corresponding to it on Earth. Still got no idea what it is. So can we find a particle of dark matter? Now, I'd like to try and explain what we do at CERN by asking you to imagine smashing 2 apples together very, very fast. And what happens when 2 apples together smash together fast is you'll get the sort of internal apple mush coming out. Now, imagine smashing those 2 apples together even faster, and not just apple mush coming out, but strawberries, bananas, raspberries, other fruit. Now, this sounds crazy when talking about fruit, but this is what happens when we smash together protons inside the Large Hadron Collider at CERN. Particles that weren't there before come out of that smashing, of that collision. They might be electrons, for example. And this all happens thanks to the most famous equation in science. Maybe you can think about it and even try and type it in chat. It's somewhere here. Wonder if you can find it. It is, of course, E equals mc squared. Now, the protons inside the Large Hadron Collider reach absolutely incredible speeds, and I'd like to ask you how fast you think it is. So, question is, how fast is an LHC proton? I've got a few options, so you can type in chat which one you think it is. Is it 1, 17,130.452 miles per hour? Is it 2, 213,200.432 miles per hour? Or is it 3, 670,616,622.678 miles per hour? So again, if you're watching on YouTube later, you can pause here if you want some more time to think about it. Otherwise, people here now can type in chat. We've got answers coming in. Some saying 2, some saying 3, some saying 1. So we've got a mixture of each answer so far. Mostly saying 3, I think. Okay. So I'm going to reveal that 17,130.452 miles per hour is the speed of the International Space Station as it goes around the Earth. Answer 2 is the fastest human-built object. It was a space probe going in towards the sun, Parker space probe, I believe. And that means that the last one is the speed at which protons travel inside the LHC, 670,616,622.678 miles per hour. That's only a tiny, tiny bit less than the speed of light. Here is a map of CERN. And what happens, or excuse me, one thing before that, it goes over France and Switzerland. That's how big it is. And what happens is that the protons start off in a bottle of gas, and then they go around this small ring, sped up a little bit, and then they go into this bigger ring, get sped up even more, and then they go into the even bigger ring, the Large Hadron Collider, to get sped up to that 670 million miles per hour speed. I'm going to talk about Atlas later. I just wanted to show it on this map. If you imagine the Large Hadron Collider, LHC, the big ring, as a bracelet, Atlas is like one of those beads that wrap around the bracelet, and the bracelet goes through that bead. So the Large Hadron Collider goes through Atlas. And just to give you an idea of scale, the Large Hadron Collider would basically go around the whole of Brighton, most of it in the sea, which actually wouldn't be ideal, digging underground into the sea. But that's just to give an idea. The Large Hadron Collider is a bit like a motorway in the sense that there's a bunch of protons going in one direction, the headlights you can see in white, and another bunch of protons going in the other direction, the headlights you can see in red. And they don't, the biggest difference with a motorway, not just that it's many times faster than the cars on a motorway, but the biggest difference is that those two paths, the paths of the white headlights and the paths of the red headlights, are made to cross over at different points along the Large Hadron Collider. Now, this would be disastrous if it was the case on the motorway. There'd be lots of crashes, but that is exactly what we want in the Large Hadron Collider. We want to smash these protons together at very, very high speeds. Now, I'm going to let my friend Savannah give you a tour of ATLAS.
Here, next to me, you can see the ATLAS detector. And the first thing you'll probably notice is that it's really, really big. So the ATLAS detector is 25 meters tall, 46 meters long, and it weighs around 7,000 tons. So to put this in context, it's taller than 5 giraffes, it's longer than 3 school buses, and it weighs almost as much as the Eiffel Tower in France. So ATLAS is constructed kind of like an onion. It has lots and lots of layers. So if we start from the center down here, as Mayrin said, we smash protons together in the center of ATLAS, and then these can produce new particles that radiate out from where we smash them. So we start by looking from the center of our detector, and then we look outwards to try and reconstruct this puzzle. So in the very middle of the detector, we have what we call the inner detector. So the particles that we're looking for have lots of different properties that we can use to identify them. So some particles have electric charge, whereas some particles don't have electric charge. So the job of the inner detector in the center is to look for these particles with electric charge. Then we build out our layers going outwards. So after the inner detector, we have what we call calorimeters. So you might have heard of using calories as a measure of energy. So we have calories in the food we eat, and calorimeters are doing the job of measuring energy of particles. So we have 2 different types of calorimeters. First, we have the electromagnetic calorimeter. So as the name suggests, this is looking to measure the energy of particles that interact with the electromagnetic force. Outside of that, we have the hadronic calorimeter. So this is looking to measure particles called hadrons. So hadrons are particles that are made up of quarks. So the most famous hadron is probably the proton. So this is what we're colliding in the center of ATLAS. And then outside of this, so you might be able to see these things with the orange stripes on. Now, these are toroid magnets. So we have this giant superconducting magnet system in ATLAS, and we use the magnets to bend the path of the charged particles within ATLAS. So why do we want to do this? So by bending the path of the particles, we can calculate the particle's momentum. So momentum is basically just a measure of a particle's speed and its mass. So this can tell us more information about the collision that the particle came from. And you might also be able to see, so we have the toroid magnets here with the orange tape, but then we also have this kind of strange flower-looking metal thing down here. And this is the end cap toroid. So this, when the detector is running, this is rolled into the center and it forms part of the big magnet system. So we're nearly at the outside of our detector now. So the outermost layers of the detector is the muon system. So muons are a special type of fundamental particle. They're very similar to electrons, which you might have heard of, because electrons make up the ordinary matter that we see around us. So muons are basically the same as electrons, but they're much, much heavier. They're about 200 times heavier than electrons are. So because the muons are much heavier, they're able to penetrate through much more matter than electrons can. So this is why we need this really big muon system on the outside of our detector to catch all of these muons that are trying to escape. So hopefully, I've got Adam, my trusty cameraman, with me today. So Adam can spin around and show you the other part of the muon system. So we'll do a swap. So hopefully here you can see what looks like a giant wheel. So this is the end cap of the muon system. So this is called one of the large muon wheels. So all of these little plates that you can see are chambers that measure when these muon particles pass through them. So essentially, that's all the layers of our detector. You might also be able to see in the center where there is this blue part in the middle of the wheel. This is where our beam pipe comes in. So as Mayrin was saying, the Large Hadron Collider, or LHC, is 27 kilometers long, and we fire the protons around it at almost the speed of light, and then we bring them to collide at 4 interaction points. So right in the center of Atlas is one of these interaction and collision points. So where this blue part is here, this is where the protons come into the detector. And then in the center, they're brought together to smash up and see what happens. So essentially, Atlas is a giant microscope built to look at the smallest fundamental particles that build up our universe. So to go back to Mayrin's apple analogy earlier, as physicists, we don't know what went on in the center of Atlas when the protons collide. All that we can see are all these smashed up bits of apple all over the floor, and then we have to come along and try and put them all back together and work out what was there originally. So we have lots of theories that tell us what we expect to happen when we smash these particles together. So we come into the experiment knowing that hopefully when we put them all together, we will build an apple again. However, the exciting thing about physics is that sometimes things that we don't expect to happen might happen. So we might come in expecting to build an apple, but find we actually build a pear instead. And then we find out some new physics, which is what we all aim to do. So so Atlas itself is a general purpose detector. So this is what we call it. And that's because it's designed to be as generic as possible and look for as many things as possible. So one of its main aims was to try to discover the Higgs boson, which was discovered about 9 years ago in 2012. And that was a really big achievement for CERN because that was one of the final missing pieces of what we call our standard model of physics. So this is basically our recipe for all the fundamental particles in the universe. So that was a really big discovery. But since then, you might say, well, what has Atlas been doing for the last 9 years then? So one of the main aims now is to really, really precisely test the Higgs boson. So we've been looking to see how it decays into lots of different particles. So the Higgs boson itself only lives for a very, very short amount of time. So we can't actually detect it inside Atlas because it decays before it's even hit our inner detector. So instead we have to find all the particles that it's decayed to and then reconstruct them to try and build a Higgs boson at the end. So as I said before, Atlas is 100 meters underground. So one of the questions you might ask is, well, how did you get it 100 meters underground? So what we can show you is that we have a really, really long shaft. So I think our cameraman now is going to try and show you without dropping the phone down inside Atlas. So hopefully you can see this really, really long shaft. So basically what happens is we have really strong cranes and equipment to bring all the different parts and the different layers of Atlas down underground. Mayrin, over to you.
Hopefully you enjoyed that tour from Savannah there.
Here.
Now, that was my really long answer to the first bit of what makes CERN special. It's that what we do there is just really cool. We're answering really deep questions about the fundamental nature of the universe. I'm going to move on to a second answer to that now and ask, who is CERN? First of all, I want to ask you, how many people do you think are involved with CERN for their work? So how many people work with CERN? Is it 1, 200, 2, 2,000, or 3, 20,000? I'm going to give you a bit of time to type those answers in chat. If you're watching on YouTube later, you can pause to have a bit more time to think if you like. Got a mixture of 2 and 3, and we've got a very nicely qualified answer by Laura. Nobody thinks 1. Okay, the answer is 20,000, but it is more like Laura says, on site. It's during a normal time, probably more than 2,000. I'm not sure exactly. probably in the upper thousands, maybe less than 10,000. But yeah, across the world, 20,000. This isn't all 20,000 people. It's a set of students over a particular summer. But what you can see is that they're all very happy. Now, not just the number of people makes it special, but also the fact that we are an absolutely worldwide collaboration. We are 110 nationalities that span all over the world. There are some nationalities missing, unfortunately, and that is a goal for the years to come, is to integrate more and more of them into CERN. So that's my second answer to what makes CERN special. It's that we are an absolutely massive collaboration that spans across the world. Going for my third answer now, you might be asking, what's the point? Why should I care? How does it affect me? And you would be quite right to ask that question. So I'm going to try and answer, what's the point of CERN? Well, in doing all of these things, trying to measure these super precise proton collisions, we have to push forward the boundaries of technology, of computing, of engineering, because nobody has answered these questions before. That means nobody has even thought about how to answer them, thought about what equipment is needed to answer them. So we have to build those things and come up with solutions. And those solutions, be they new technologies, new ways of engineering, new ways of doing computing, make their way into everyday life. And I'd like to give you a few examples. First of all, many medical technologies were developed and even invented at CERN. For example, this is a brain scan that uses some technology that was initially developed at CERN. And another example is the World Wide Web was invented at CERN. And I think you will find the World Wide Web pretty useful. So that's my third answer to what makes CERN special. It's the technologies that come out of it. And for my fourth answer, I'd like to ask, what's the future of CERN? And for that, I'd like to come back to this. The answer to that question is students and young people. They're the future of CERN. And that's the fourth thing that makes CERN special, is its dedication to training and educating young people while studying there. Many students can go to CERN to be summer students over a summer. They can do their master's research there. They can do their PhD research there, like me. And the training is not only in particle physics, of course it's in particle physics, but it's in other skills, such as how to work with computers, how to work in an international environment, how to work in a big team. You know, people can take on leadership roles. People can learn about machine learning, artificial intelligence, how to program computers to tell them what to do. And these are all skills that are very important in society right now, but will become even more important in society in the years to come. We will become even more reliant on computers, and we will have to be even more globalized and cooperate with each other. For example, the situation we find ourselves in illustrates that nicely, that we need to cooperate to move forward. That's my fourth answer to what makes CERN special. Now, to summarize, what makes CERN special is that we are answering really deep questions about the universe using the world's largest scientific collaboration and building technologies that benefit everybody. For example, in the background here is a vacuum technology that's being used on some solar panels to increase their efficiency and therefore use less energy in an airport. And that technology was developed at CERN. And last but not least, and definitely most, is the fact that CERN is training citizens of the future. And that's it. Thank you very much.
Thank you, Miriam. Much appreciated. Really good insight to the work you do at CERN. You must be missing the place because a year ago you'd be going there. Well, how often will you go?
Every day. That's where I was working.
And now you're stuck in the UK.
Yeah.
Yeah. If you have now Q&A sessions, so if you do have absolutely any questions whatsoever, feel free to put forward your suggestions. Either send me a message in the chat. I'm looking at the chat box now, or feel free to raise your hand, and you're welcome to ask Miriam directly. One question we've got come up in the chat already from Paul. What and when is CERN working on next? So what's the next? I guess the main motivation for CERN was discovering the Higgs boson. What's next?
Thanks, Paul, for that question. Well, the answer to the when part is now. As we speak, many people across the world are analyzing data from CERN. And for the what, it's I try to illustrate some of the main questions that CERN is trying to answer. For example, where's all the antimatter in the universe? And is there a particle corresponding to dark matter? Is there anything smaller than quarks? Those are all principal questions trying to be answered by CERN.
Okay, another question from Rosanna. How is CERN funded?
That's a good question. Thank you, Rosanna. The answer is all of the member countries of CERN pay a certain percentage of their GDP. I can't remember the percentage, but it's very small. So a country such as Germany that has a high GDP will pay more into CERN from taxpayer money than a country like Poland that has a smaller GDP. And to put it into context, CERN costs each taxpayer in the member countries a cup of coffee a year. You can say this because a cup of coffee in Germany will be more expensive than a cup of coffee in Poland. So I for one, am pretty happy to sacrifice a cup of coffee a year for CERN to continue.
I tend to drink tea, so that's fine by me.
Easy.
Another question from Paul. Assuming the dark matter is a particle with only gravitational interaction, the weakest force there is, could CERN detect it? So yeah, do you think CERN will be able to detect dark matter?
A great question, Paul. Well, the answer is we really hope so. Now, at present, it wouldn't be able to detect dark matter if it only interacted gravitationally, because gravity is just so much weaker than the other forces. That also explains why we haven't found a graviton yet. But the hope is, and it's not just a hope, it's in many theories, is that dark matter also interacts through the weak force, which is weaker than the strong force and the electromagnetic force that are responsible for most of the collisions or smashings that happen at CERN. But there's also the weak force that's a little bit weaker than those two and may be able to give insight into a particle of dark matter.
Yeah, if you want to do an experiment to see how weak gravity is, to jump up and down a bit. Another question from Jamie: will CERN generate a black hole?
Everybody loves this question. Will CERN generate a black hole? Thanks, Jamie. So the answer is no. Sorry to let you down. Now, popular media were saying it might before the Large Hadron Collider started, and that's because there were some theories that said microscopic black holes might be created. They weren't. Most people didn't think those theories would be proven experimentally, but those theories were still out there. And anyway, even if those theories were correct, any black holes created would be microscopic. And I don't mean small enough to be seen by a microscope. I mean way smaller than that, smaller than atom size. And what that means, the fact that they're microscopic, means that they evaporate almost instantly after being created. So there wouldn't be any time for them to suck in anything and suck in the Large Hadron Collider and suck in anything else. So there's nothing to worry about for black holes. And anyway, even if these theories were correct, there are higher energy collisions that happen in the top of our atmosphere, and they've been happening for as long as the Earth's been there, so 4.5 billion years or something like that. And none of those collisions have ever created a black hole, and they've been happening for much longer and at higher energies. So if they can't do it, then it definitely can't be done at CERN.
I do love the fact that while CERN is the most powerful instrument humans have ever generated, nature is well ahead of us, and nature producing even more violent collisions at what, about 20 kilometers above our head, something like that. And also, I'm an astronomer, so anything smaller than 3 or 4 solar masses, can it be called a black hole? Anyway, before I go off on one, a question from Laura. Are the protons that are passing through the Atlas detector degrading the panels and degrading the instrumentation?
Yeah, very good question, Lara. The answer is yes. And we go through what we call shutdowns, where we maintain and upgrade the experiments. And that is exactly what's happening at the moment at CERN. That's why my friend Savannah could go underground and give you the tour. When the Large Hadron Collider is smashing protons together, you can't go underground. And that's precisely what the shutdown is for, is to fix and upgrade, maintain the equipment, because they've been degraded from all the particles passing through them.
Yes, a very good question there. What impact, another question from Laura, what impact could detecting dark matter have?
Another good question, Lara. Well, the answer is simply we don't know right now. It could have a huge impact. It could lead to another world-changing technology, such as the World Wide Web, or it could lead to another technology that saves lives. But right now, we don't know. Those sorts of technologies come decades after the discovery of a particle. For example, PET scanners, PET, it's some medical technology to image the body. They use positrons, and positrons are the antiparticle of electrons, which were discovered in 1932, I believe. And PET scanners, I don't know exactly when, but they were probably developed, I don't know, in the 90s, maybe 2000s. So that illustrates that uses and applications and technologies that use new particles come decades into the future. So I'm not saying there will definitely be a new technology that saves lives thanks to dark matter, but it's a possibility.
I love the story behind PET scanners, in that if you go back 100 years ago, there was a theoretician, an English theoretical physicist called Paul Dirac, and he was playing with equations, and he had a square term in one of his equations, and he realized that you could have a negatively charged electron, because if you have negative charge and square it, the negative disappears. But you can also have a positive charge as well. And then, as Marion said, a couple of decades later, we are now using, the local hospital is making positrons every day to look inside cancer patients to help exactly find out where cancers are and treat it accordingly. We'll take two more questions. I'll finish in about 2 more minutes. So yeah, let's just take a couple more questions. Oh yeah, another impact that detecting dark matter would have is to make astronomers very happy, because
That's important as well.
yeah, at the moment, it just makes us all a bit uncomfortable, this dark matter, and it makes no sense, and we just want to know why it is. What's the most mind-boggling thing you have learned or experienced in your time working at CERN?
Yeah, that's
a great question.
Yeah, agreed. For me, it was the first time I got to go underground. You go down some stairs, and your view is kind of blocked by that flowery big wheel that Savannah pointed out. So you go down the side of that, down some stairs, and then you can turn around a corner to go past that big wheel, and then you see that view that you had during the tour. And that was just amazing for me. I'd been using the data from that experiment for years, and seeing it gives you an extra appreciation of, man, what I'm doing on my computer comes from there. And you still don't understand every step of the process that gets the data from that collision to your computer, but it just makes you appreciate it even more. So that was the best experience for me. The first time I went underground, turned the corner, and saw that view that you had with my own eyes.
Big toys. Okay, final question for this evening then, from Laura, who's going to ask you the forbidden question. What's your specific area of study?
Thanks, Laura. It might be the forbidden question, but I don't mind answering this. And I'm going to answer it with an analogy, saying that in particle physics, what we do at CERN, there are essentially 2 avenues of what's next, as somebody asked earlier. Now, one avenue is what we call searches. Imagine collecting together all of the animals in the world and throwing away ones you already knew about. Keep throwing away. So you've seen a giraffe before, throw that away. Seen a rhino before, throw that away. And what you're left with is things that you haven't seen before, species that you've now discovered. The analogy being, we collect as many proton collisions as before, see what comes out. If we've seen it before, throw it away. Are we left with anything that we haven't seen before? That's a search trying to find a new particle. The second avenue is called a measurement. And in the analogy of animal species, let's maybe look at the rarest animal species that we have found before. I don't know what that is in animal species. Let's say, I don't know, a really rare tiger. And let's study that in great detail, ask questions about its characteristics, and maybe those, when we study it in great detail, those characteristics will lead us to more questions like, is there a different species with that characteristic, but even greater? is there some cousin of that rare tiger that we haven't found of before? And then we'll have a better idea where to look for that even rarer tiger cousin. That's called a measurement. Now, I'm doing a measurement with the top quark, and the top quark is interesting because it's the heaviest particle we know of. That's sort of like doing research on the heaviest animal species, which would be interesting in itself to ask whether there are other animal species we haven't discovered yet that are even heavier than it, for example. So like studying the humpback whale, for example. Hopefully that answers your question. So I study the top quark, make very precise measurements of it.
And that was a really good analogy. Thanks for that, Mervyn. We've just about run out of time for questions, but if you do have any more questions, feel free to email Mervyn. You can see his email address there, so feel free to send him lots of further questions. So yeah, thank you very much. Thanks for joining us, everyone. And thank you, Mervyn, for telling us all about apples and pears and various animals and a little bit of physics as well. So yeah, thank you very much for coming, and thank you, Mervyn.
Thank you.
I'm not quite sure when the next Sussex Universe talk is, but it's all online, so do take a look and keep up to date on the website. Thank you, everyone, and good night.